high energy gamma rays in the energy range that goes basically from several tens of GeV to several hundreds of TeV. And Ctools is an open source community developed software package for the scientific analysis of data from this kind of telescope. It is based on GammaLib, which is a generic toolbox for scientific analysis of astronomical gamma ray data, which has support for IACTs, but also for Fermi-LAT, CONTEL, and Integral, so satellite detectors that cover lower gamma ray energies that go from several hundred of TeV to several hundreds of GeV. It was validated so far on simulated data and on real data from Hess and from Fermi. And here you have the reference of the latest paper on validation. All the information is available on the Ctools website, which is given here. And in particular, the parts that may interest you are how to get them, how to use them. There is actually a very comprehensive manual, some tutorials, and a detailed description of all the tools. And you can also contribute to the development. The latest release of Ctools was 1.7.4. Let me mute the notifications from Skype. Sorry, I forgot to do that, and now they are bothering me. Okay, so the latest release was 1.7.4, but there is also a development version that you can have access to if you want to exploit the latest features. This scheme here gives you an overview of the tools that are available in Ctools that are aimed at covering several different parts of a data simulation and analysis. The first part is the data themselves. So first of all, Ctools is a high-level analysis software that aims at analyzing event lists, which means data that have already been analyzed at the event level, so that you have selected events with a relatively high probability of being photons, and you have already determined their energy and their arrival direction. So you have a list of these candidate photons in FITS format, which is the standard format used in astronomy. And on top of that, you have metadata such as the pointing direction, the lifetime. You have a list of good time intervals, which is the continuous intervals of data taking with stable instrument response. And these event data are in a format that has been established by a community working group. You have the link here at the bottom of the slide. And the fact that the future data from CTA and data that are made public by current experiments such as Hess are all distributed in this very same format means that you can analyze all of them using Ctools and any other software that uses this common data format. Here you have a snapshot of what you have if you open one of these event lists. I'm sorry, there is someone with their mic open and I hear background noise. Okay, I think it's fixed. Here you have a snapshot of what these event files look like if you open them with FitView. In Ctools, you can also use multiple event files that have been combined together in an observation list that is serialized using the XML format. This is shown here. This is what one of these XML files looks like. If you open it, in fact, you don't need to really manipulate this kind of files. This is done all automatically, as I will be showing later. The other ingredient that you need in order to exploit the data beside the event lists is the instrument response functions, which are the mathematical model that tells you how you convert the flux of photons arriving at the instrument in terms of true photon energy and direction into the number of counts that the instrument detects in measured photon energy and direction. And conventionally, these instrument response functions are factorized in 3 terms that are effective area, point spread function, and energy dispersion. This information is also stored in FITS files. So once you have the event data, you can perform different operations. You can inspect them, you can select them, you can bin them. But at some point, to perform a scientific analysis, you also need a model of the sky that you will compare to your observations to constrain some of the model parameters. This model needs to include the gamma ray sources that are observed, but also the residual background that comes from cosmic ray interactions with the atmosphere. So in Ctools, you will find some tools also to deal with the construction of the model. In general, each model is split or decomposed into 3 different components that are the spatial part, the spectral part, and the temporal part. You don't always need the 3 of them, but in general, you may have them for a model. And in Ctools, these models are also serialized for writing to disk using the XML format. Once you have your model and your data, you can compare them through analysis that can be done in several different flavors that are represented by the boxes on the bottom of the slide. You have imaging analysis, spectral analysis, timing analysis, likelihood analysis, and on top of that, you have some utilities. And I will be explaining more in detail how the analysis works in the following slides. But before we do that, would you have any questions you would like to ask right now? Okay, so I will move on for the moment. Yes, please go ahead. Do you want to ask a question?
Hi. Hi. Have a question.
Yes.
Can you go back to the previous slide, please? About this model preparation, maybe I don't know if I am understanding well what you mean with that. It has to do with a particular model that I have. I mean, if I have a dark matter model in my Lagrangian, let's say, it is related with that or nothing to do?
Okay, it's a very good question, actually. The type of model that we deal with at the Ctools level is actually a model that has already been converted into photon space, meaning it needs to be a model that gives you, for a gamma ray source, the flux of photons that is arriving at the Earth as a function of direction in the sky and energy and time in case. For background, it needs to be the number of expected, the expected rate of background counts as a function of direction in camera coordinates and reconstructed energy. So it cannot be directly a physical model like a Lagrangian of a dark matter model. But if you have your physical model, for example, of dark matter, you can convert it into expected photon flux as a function of direction and energy so that it can be digested by Ctools. For the moment, there is nothing in Ctools that takes care of that for you, but there are people that have been working to do that, and we will see that in the following part in the exercises.
All right, perfect. Thank you.
Okay, thank you for the question. Are there any other questions so far?
Yes, I have a question. One.
Yes.
So at the end of the pipeline, okay. So sorry, I got the answer. My question was related with the image analysis. Okay, sorry.
Okay, no worries. In general, I didn't say that explicitly. Perhaps it's worth saying. Here you see blocks that are generic, but each brick, each tool can be used independently. So what you can do is that you take the bricks or the tools that you want to use and you combine them in the order and in the variety that you want to, so that you build your own pipeline. You know, it's not like a fixed thing. You need to go always through the same blocks in the same order. You can take the individual bricks and rearrange them as you want. Is there any other question? Okay, so going on, the analysis method. The core analysis method that has been implemented in Ctools is the likelihood method that many of you may have already heard about because it's used vastly in physics and astrophysics. But here I just summarize the idea. The idea is that you have the actual sky and you have a model of the sky that may have some free parameters. You observe the sky with your telescope and you end up with having some candidate photons. At the same time, you can perform Monte Carlo simulations of your telescope so that you have a model for the response of the telescope, which can also be fine-tuned using the data, which is what finally yields the instrument response functions. You can use the instrument response functions to forward fold the model into count space. So you have the model predicted counts. And at that point, you can compare the candidate photon counts with the model predicted counts, compute the likelihood of a given model, and determine the best fit values and uncertainties for the model parameters. In Ctools, there are different ways that you can do that. First of all, there are the so-called classical IACT analysis that as guiding principle have that you constrain the background in dedicated background regions that are also called off regions. And you identify a dedicated source or on region and the background or off regions. So this is illustrated here in this map. This is the observation of a bright source, as you see. So we define an on region, which is where we have the signal from the source, but we will also have some background. So we define some other regions that are called the off regions, where we have only the background. And we can constrain the background and the source at the same time. This is illustrated on the right, where you have on the top the count spectrum in the region on, where you have the source. And so you have both the model, which is called the signal, which is called Crab, because this was a simulation of the Crab Nebula, and the background. And on the bottom, you have only the background because it corresponds to the off regions. This is similar to what is done in X-ray analysis often, and it implies to have a separate imaging and spectral analysis, which are done in 2D and 1D space. The strength of this classical IACT analysis is that you have fewer assumptions on the background with respect to what I will be showing later, but you sacrifice some information. For example, you see that here, everything that is outside the on and the off region is thrown away. And the information of the direction within the on or the off regions is also thrown away. When you use this analysis method over multiple observations, you can do two different things. That is either performing a joint analysis, which means that each observation is treated independently, and you just combine them at the level of calculating the likelihood, or you can perform so-called stacked analysis, where you just sum the count spectra from all the observations together. The alternative to the classical IACT analysis is 3D analysis, in which you model background and sources together over the entire region of interest in 3D space at the same time. So 3D means sky direction plus energy. This is a technique that is very often used for satellite gamma ray detectors, and it has the advantage that you can exploit the full information in the data. You don't throw away anything, basically, and you can handle multiple overlapping sources. But for this, you need to have an adequate model to describe the background, which is not something that is always guaranteed. There are two different ways in Ctools that you can perform a 3D analysis. One is bind, where you basically build maps of the counts in sky direction for different energy slices. And the other is unbind, where you really take into account arrival direction and reconstructed energy for each photon. For the bind analysis, when you have multiple observations, you can deal with them in the same ways as I described for the classical IACT analysis. Before I move on, are there any questions on this just taster that I gave you on the likelihood analysis methods in Ctools?
I have one question, but not with this light analysis, but the files that are used for analysis, can one Fermi Fitts file also use with Ctools?
Sorry, I didn't get the question. What kind of files?
Fitts file from Fermi data, Fermilab.
Yes. As I said at the beginning, there are modules in GammaLib that deal with LAT data or integral or contel. So if you have, for example, count cubes for the LAT, you can pass them to Ctools as well.
Yeah, okay. Thank you.
In the validation paper that I mentioned above, you will find an example. We analyzed at the same time the LAT and the HESS data for the Crab Nebula and derived the spectrum over a large energy range using this method. Are there any other questions? Okay, so let me move on. Here we get closer to the practical aspects. That is, how do you use Ctools once you have installed them on your machine? There are actually two different ways, and you can choose. It's exactly the same. There are just two interfaces. The first interface has executables. So they are command line executables that you call from the command line. This is illustrated here on the top. Here, for example, I use as an example a tool that is designed to simulate IACT observations. It's called the Ctopsim. You see, you call it from the command line like that. And then there is an interface that will query for the relevant parameters. For example, if you want to simulate an observation, you will need to specify where you are pointing your telescope at. So in this case, the tool will ask you for the right ascension and the declination of the pointing. And you see that you have a default or latest use value. This is called an automatic parameter because it's automatically queried when you launch the tool. If you have an automatic parameter, you can change the default value by specifying another one, as it is done, for example, here for the right ascension. Or you can just click enter, and in that case, you will just be using the default or latest used value, which is what is done here for example, for the radius of the field of view to simulate. There are some more parameters that are called the hidden parameters, which are not inquired automatically, but you can still specify them from the command line. For example, here I had specified that I want that energy dispersion is taken into account in the simulation. Once you have finished specifying all the parameters that are required, the tool runs and produces some output that then is on disk, and you can inspect and you can pass to following tools. The command line executables can be used from the command line, but for example, you can use them also in shell scripts if you want to script in your shell. The other interface that you can use is the Python API. So Ctools is accessible from Python as a package, as a Python package, which means that you can use it from a Python terminal, in Python scripts, or in Jupyter notebooks. And here I have done exactly the same thing that I have done above with an executable, but from the Python API. So you see that in this case, you need to create an instance of the tool, which is what is done in the first row here. Then the instance of the tool has a dictionary, a Python dictionary, that corresponds to the values that you want to assign to the parameter. So you fill the dictionary with the parameter values that you wish to use for your task, and then you can execute the instance so that you have the same results as from the command line. Are there any questions on this? All right, so let's go ahead. So now we have finished this quick presentation that was just meant to give you a quick overview of what is Ctools, what is the working principle, what are the analysis methods that are available in Ctools, and how you use Ctools concretely. The next part, the next 20-30 minutes, let's say, will be a demonstration, a practical demonstration on how you use Ctools. And for this, I will be running a simulation and analysis of CTA observations of the Crab Nebula. The following part will be some hands-on tutorials where I will ask you to do yourself some exercises. And I prepared a range of exercises that you can choose from, depending on your level of experience with IACT data analysis, Ctools, and your interests as well. So they are 6, and they are written here. So one thing that you can do is to revisit the demonstration that we had done, that we will have done together by playing with different analysis configuration or parameters. There is one exercise on background modeling, one on extended sources, one on more advanced model manipulation and fitting, and one on dark matter models. There is, of course, also the possibility to explore your own science case. Some practical details for that part that I wanted to share right away. The exercises are provided as Jupyter notebooks, as it is the demonstration that I will be running. You are not obliged to use the Jupyter notebooks. If you prefer writing scripts or running from the command line, it is also possible. Each notebook is also available as a PDF so that you can see the guidelines and use that to do the exercise in any other way. There are a couple of exercises that require to have the public hash data. You got the instruction on the school web page on how to retrieve them. So if you want to do those exercises, you need to use the hash to retrieve the hash data if you have not done it already, and use them. And final word, start thinking about which exercise you want to do, because we will try to split you in breakout rooms later according to the exercise that you are doing, so that we can more easily interact between us and also you with each other. Also, very importantly, there is one of the students attending the school, which is Sergio, that has actually a lot of experience with using Ctools, and especially for dark matter studies. So he agreed to help with helping people during the session. So we will also become a coach during the hands-on part. Finally, well, one warning is that I guess that given the topic of the school, many of you would maybe be tempted to jump on exercise number five, constraining a dark matter model. I don't want to discourage you if you want to do so, very good, but I would not recommend it for people that have never run a gamma ray analysis before or never used Ctools before, because it's a more advanced exercise. So if you have little experience in gamma ray data analysis or using Ctools, I would rather encourage you to do one of the exercises with a lower number. Finally, another practical thing I wanted to mention is that I will be able to join the Gather Town after 5:30. I will not be able to stay probably for the entire hour and a half, but at least the first hour. Are there any questions from your side on the practical steps for the rest of the session, or any other questions that you would like to ask now?
I have a question.
Yes.
Could you elaborate maybe on the difference between number 2 and number 4?
Number 2 is focused on background. So the event samples that you get from imaging atmospheric Cherenkov telescopes are always contaminated by some residual of cosmic ray interactions with the atmosphere. So exercise number 2 is focused on how you take care of that background contamination. Exercise number 4 focuses rather on gamma ray sources. So how you improve your model for the gamma ray sources, how you test which model is better.
Okay, so is number 2 more of an on-off analysis, or is it also based on more concrete models?
There will be both.
Okay. Okay, thank you.
Are there any other questions?
So for you said for beginners, you recommend number 1 or number 2, right?
Or maybe number 3 also.
Okay. Oh.
It depends which kind of beginner, right? It depends if you have a previous experience in gamma ray data analysis, if you have ever used.
In my case, I don't have any experience on that, but I work on dark matter, so I am tempted to go to 5, but
Okay.
I don't know.
Honestly, if you want to do it, go ahead. I wouldn't do it first. I don't think it will be extremely productive, because you will not be able. My recommendation in a case like yours would be to take number 1 or maybe number 2 or 3. But you know, the notebooks are there, so you will be able to do the exercise on dark matter later if you want to.
Sure.
And we'll be in touch, both Sergey and myself. So if you do that later and you have questions, you need help, you will get it. It's not a problem.
Okay.
As a first exercise today, I wouldn't jump on it.
Okay, thanks.
Any other questions? Okay, so let me get to the demonstration. In this case, I will share another thing, which is a Jupyter notebook. Let me see if I can find it in my. Okay, give me 1 second. Yes, sorry, too many windows open. So there you are. Okay, So this is done using a Jupyter notebook. I guess that many of you may already have used the Jupyter notebooks before and are familiar with it, but otherwise it is just an interface to use Python, more or less. The nice thing is that you have also text that is interleaved with the Python code, so you can have instructions, comments, and so on. If you have questions, do not hesitate to interrupt me at any time, okay? So the first thing that you want to do when you use Ctools from Python is to import the relevant Python modules. So here we have 3 that are imported, which are all related to Ctools, which is GammaLib, the basic library, Ctools, and Cscripts. As far as you are concerned, don't worry about the difference between Ctools and Cscripts. There are these 2. The difference is how they are developed. Ctools are C++ code, Cscripts are Python scripts, but at the end of the day, you don't really care. Here, I also import matplotlib, which is a plotting library for Python that I will be using for visualization. So as I said, in this demonstration, we do a simulation of observations of the Crab Nebula, a very bright gamma ray source with CTA, and then we analyze these observations. So this is what I already started introducing to you, how you perform a simulation. So there is a tool in the Ctools suite that is dedicated to simulations, which is called Ctopsim here. So the first step is that you create an instance of this tool, which I call sim here, and then you fill the dictionary with all the parameters that need to be set. On the website, there is a part of the Ctools manual that is called the reference manual, where for each tool, you can find the parameters that can be filled. Later, I will show you that you can also retrieve that directly from your computer, but to start with, you can take a look at the reference manual. Here you see that the parameters that I am setting are the input model. Here we use an example that is shipped with Ctools that contain just a simple model for the Crab Nebula and the background. You need to specify the name for the output event files. You need to specify the response for CTA that you want to use. Here I use the latest public CTA IRFs, which are called 3BV2. And I use the response for the southern CTA array at the zenith above the horizon of a zenith with respect to the an inclination with respect to the local zenith of 40 degrees, and the response functions that were optimized for observations lasting half an hour. I specify the right ascension and the declination of the observations, the opening of the field of view that I want to simulate, 5 degrees, the start and end time for the observations. So you see here I simulate an hour of observation, the minimum and maximum energy, here from 30 GeV to 150 TeV, and I use energy dispersion. And here I execute the tool. So let's do this. This will take a few seconds. Here it is. Now the tool has been executed. We have the results. Before looking at the results, I wanted to also tell you that, in fact, from the command line and also from, yes, question, Miltos?
Yeah, I just wanted to ask, what is the maximal zenith angle of the Crab Nebula from the southern CTA side?
I don't remember this on top of my head, to be honest.
No, I'm just wondering, because most probably this is the reason why you choose the 3BV2s at 40. So this is what I wanted to see if it is just compatible or if it is just an example. This is what
it is certainly compatible. Okay, so first of all, right now we don't have evaluations of the CTA instrument response functions for arbitrary values of the zenith angles. We have only 3 possible values that are 20 degrees, 40 degrees, and 60 degrees. The Crab Nebula from the south is certainly observable at something that is close enough to 40.
Yeah, this is what I wanted to ask. Thank you.
Yeah, when you do this type of exercise, indeed, it's very important that you select a zenith angle for the instrument response functions, which is something that is close enough to the actual observing conditions, because the zenith angle is a very important parameter in determining the performance of the observations. Thank you for asking this question. The next thing that I wanted to show you indeed is that you can get from the command line or within Jupyter notebooks informations about the tools, so that, for example, you can know which parameters you need to specify, and this is done through the help. So here the exclamation mark just means that I call the tool from the command line, and here I'm using the help function of the tool. So if you see that if I do that, I get a description of the tool. So it tells me simulate the event lists, and then there is a synopsis that gives you more detail on what the tool does, what the output is, and so on and so forth. And then you get a description of all the parameters. For example, you see InModel is an input model XML file, CalDB is the name of the calibration database, and so on and so forth. So the first time you use a tool, you can use this to discover which parameters you need to specify and how the tool works. Okay, now let's look at the observations that we have simulated. So our instance of the simulation tool is called SIM. Each tool related to observations has a NOPS method that enables us to access the observations. So let's look here. If we do that, we see that we have one observation which has two models. We have 800,000 events, and the instrument was CTA. The event file is named event fits, and so on and so forth. We can look more in detail into the first of the observations that we had obtained, which is the only one here, and this is the information that come in the second part. Another thing that we can do in order to have a sense of what is in our observations is just to look at the count spectrum, that is the number of events as a function of energy. And this is done here. We can access the events as it is done here. So you see that the first observation, which is also the only one in our observation container, has a method that is called events that give us access to the events. And then here I use matplotlib to create a count spectrum in log space, where I just read the log 10 of the energy in TeV for each event, and then I do a histogram. And here you see the result. So you see that our events approximately follow something that looks like a power law, and so on and so forth. After either simulating or retrieving real observations, one of the first things that you want to do typically is to select the events. And you might want to select based on different criteria that are, for example, to have a certain time interval or a certain energy range. You can do this using another tool, which is called CTSelect. So here I create an instance of CTSelect. I fill the relevant parameters, which are the name of the event file. We had called our output event file before events.fits. So now I am feeding to CTSelect events.fits, and I am selecting events in a smaller field of view of 3 degrees, a shorter time interval that only lasts 30 minutes, a smaller energy interval that is only from 100 GeV to 100 TeV, and executing my event selection tool. Once we have selected our events, we can look into them again. So in this case, I look at the observations that are tied now to the event selection tool. And you see that the number of events has been largely reduced by our selection. We have only 140,000. And you can still have all the information on the on-time, lifetime that have also changed accordingly to our selection. A thing that is very interesting when you use Ctools from Python is that there is no need actually to write stuff to disk. Right now, we have used the tools as if we were on the command line. So we have written the events to disk in the events.fits files, but we don't need to. We can keep everything in memory. And I am showing here how to do it. Basically, rather than using the execute method at the end that run the tool and writes the output to disk, you can simply use the run method. Also, this is interesting because in Python, rather than passing the input observations using the inobs parameter, you can directly pass the observation container in the constructor of the tool. So here I redo the selection, but this time I pass in the constructor the observation container that comes from the simulation tool, and then I run. And now, once this is done, which is also very quick, you can see that this produces exactly the same results. And here I am printing the models. This is something that is interesting because the observation containers already have tied to them a model. And in this way, you don't need to propagate observations and models separately. So here you see we have just the models that were used for the simulations. Basically, we have the Crab Nebula, which is modeled as a point source at a certain direction and with a power law spectrum. And you have a model for the background, which is given by a power law spectral correction with a normalization set to 1 and the spectral correction set to 0, and a constant model that is taken by the IRFs. Are there any questions so far? Okay, yes?
Can I ask something? Is there a limitation of using this instead of writing to disk? At some point, it's probably slowing down the computer, or?
Well, if you have very large data sets that you are analyzing, of course, when you get close to the memory limits of your machines, it will become slower. So in some cases, it may be convenient to write to disk, even if you work from Python, so that you easy the footprint on the memory of the computer, and that each time you load only the data that you need.
Okay, thanks, but that's a nice feature.
Okay, so going forward, typically the first thing you do once you have some data is to create a sky map and look what is in your data. There is a tool that is that is in Ctools that you can use to do so. It's called a CT Sky Map. So here I use it again using just the in-memory features. So I pass to CT Sky Map the selected observations. Then I specify the parameters of my sky map. I will make it in celestial coordinates, Cartesian projection, centered at a certain position in the sky with a certain binning in direction, in energy. And I will not apply any background subtraction. And then I run the map creator tool. This is super fast. And now we can look at the event map. I look at the event map using, again, matplotlib. All I need to do is to access the count map itself, which is an attribute of the sky map selection tool. And I won't comment very much on the rest because it's just matplotlib fair. So we can look at the sky map, and here you see that indeed we have a bright source at the center of the field of view that we have simulated, and then we have in the rest of the field a lower counting of background. If we want, we can subtract the background. There are different ways to do it. Here I illustrate how to do it in a way that is a part of the classical IACT analysis, which is the so-called ring background. So I started running this because I thought this may take long, but in fact it didn't. So you see, in this case, we do the same as before. So we pass the observations to CT sky map. We specify the parameters of the output map, but here we ask CT sky map to perform background subtraction using the ring method, which means that for each position of the map, we take a background region, which is a ring that is centered on our position, and we evaluate the count rate in this ring, and then we subtract this count rate from the on region, which is the position in the map which are interested at. We need to specify the radius of the on region, the inner and outer radius of the ring, and the number of iterations. Why do we iterate? Because of course we know that in our sky map there is some signal. So when you look here, for example, up here, if you try to evaluate the count rate for the background with a ring that encompasses your source, your background rate will be biased. How can we deal with that? Well, we can deal with that iteratively. That is, we do it the first time, then we look at where we have potential signal, and in the next iteration, we don't use that region anymore to evaluate the background. And we do this a few times, and until the results are stable. So here I had used 3 iterations. Now let's look at the background subtracted sky map. Now you see that basically you have only the source at the center, and then in the rest of the map you have some fluctuations because we have subtracted the background, but there are positive and negative fluctuations, of course. Are there any questions on the sky map part? Okay, so we can proceed with the next part. The next part is a spectral analysis, which is done using the unbind method. So this is a 3D method where all the properties of the, there is something in the chat, I believe. How can I decide the number? Sorry, okay, I see that Sergio has been answering 2 questions in the chat, thanks. I didn't see them. The number of iterations is something that you need to decide based on the results themselves. Meaning, if you do too few iterations, you will see in the results that the background is not properly subtracted. You will see something that is not compatible with being flat outside the positions where there are sources. But of course, it's something that you do on a completely empirical way. Okay, so back to the unbind analysis. This is one of the possibilities to perform a spectral analysis, and it is a 3D analysis in which for each photon you take into account the measured direction and energy. This is very easy to set up because the only thing you need is the photons and the models. So we already have all of it in our selected observations. So we can just use the likelihood tool, which is called CT-like, constructed using the selected observations, and then run it. And that's it. In this way, you can perform an unbind analysis. We can check the status of the likelihood optimization. Here you see that the optimized value for the function, which is the log likelihood, is this one. You see that the optimization has converged. You see the number of parameters, the number of free parameters, the number of iterations that were performed. And the optimization was successful. We can look at the fitted models. So you can see now that we have, for the models that were free in the analysis, which are the prefactor and spectral index of the Crab Nebula, we have now the fitted values with their uncertainties. You can see by looking above that they are compatible with the input values. And we have also fitted a prefactor and normalization, spectral tilt for the background model, and you see that the normalization is compatible with 1 and the spectral tilt is compatible with 0, which means that our background is compatible with the input background, which is obvious because we are analyzing with the same models that we used for the simulation. A very important thing when you do a likelihood fit is to check the residuals, because the likelihood value itself does not tell you anything on the quality of the fit. So you need to check how the model, the fitted model and the data compare. So we have tools in Ctools to check the residuals. The first thing that I check here is the spectral residuals that are checked using a tool called CS-ResSpect, so residual spectrum. I pass the observations and models for the likelihood fit, and then I ask the tool to compute the residuals in significance. And in this case, it's easier to plot using a fits file, so I do that. For the moment, I'm not masking the residuals, meaning I'm looking at all the events that were analyzed, and I am choosing to display the individual components on the model. The residual computation is the part that takes a bit longer. Once this is done, we will be able to display the results using an example script that is also shipped with Ctools, which is called plot residuals, to which we feed our fits file produced by CS-ResSpec so that we can see the results. So this is admittedly the longer part. Are there any questions that you would like to ask while we wait for the results? Okay, we have the results. Let's look at them. So these are the results. Here in the top panel, you have the counts that are the points, and you have the total model, which is comprised of the model for the Crab Nebula in blue and the model for the background, which is in orange. And you see that if we look at the entire region, basically we are largely dominated by the background. You see that the fit was rather good. All the residuals are within ±2 sigma. One thing that is important to do is to check that our model is good not only over the region in general, but also in every spot of the region. And you can do that by looking at the spectral residuals at specific points. Here, for example, I am going to check at the position of the Crab Nebula itself. So you see I specify now that I want to apply a mask to the calculation of the residuals. And this will be a circular region, essentially, in which we will look at the residuals at the position of the Crab Nebula itself with the radius of 0.2 degrees. And again, I will be looking at the components. And in this case, I am calling the plotting routine directly. So once this is done, we will see the residuals. Are there any questions while we wait for this to complete? The reason why it takes so long is that the residuals are always binned, as you see. And in this case, we are working with unbinned data. So internally, the first thing it needs to do is a binning, which takes a little time. So here now you have the residuals in the region of the Crab Nebula. Oh, question in the chat. Well, the difference between the two is that above I was looking at all the events. Here I'm looking only at the events within 0.2 degrees from the Crab Nebula. So I will see how the model is doing in the region of the source. Here you see that now the counts are totally dominated by the source itself. It's the blue model that dominates. And again, the residuals are pretty good. Here there is a deviation that reaches almost to 3 sigmas. But remember that we did not optimize the model over the specific region of the sky. It was optimized over the larger region that we looked at before. The other way that you can inspect the residuals is by making a map of the residuals. In this case, you sum over all energies, but you look at the spatial distribution. So the tool that is going to do this is called CS res map. Again, I build it with the observations from the likelihood analysis, and then I specify the parameters of the map, center, energy range, and the way I want to see the residuals. Here I chose another algorithm that is called subdiv, which means that I see the residuals in units of fractional residuals. How many percent do the model deviates from the data? Again, I can plot this using matplotlib as I did before for the count map. And you can see that here we have the residuals that are fluctuating between plus minus 30%-ish, and that the residuals are rather flat over the analysis region, which means that our model reproduces the data well. Are there any questions on the residual calculation? Okay, the last part that I wanted to look at is how to perform a classical on-off analysis. Here we will focus, we have already seen how to calculate a background subtracted map using the on-off technique. Now I wanted to focus on how to derive a spectrum using the on-off technique. In this case, before going to the likelihood analysis itself, you need a preliminary step, which is calculating the count spectra in the on and off regions and calculate the on-off response. And this is all done by a tool which is called CS-PHA-Gen. So we use CS-PHA-Gen starting again from the selected events that we had defined above. You need to specify the energy binning. So here I do logarithmic binning from 100 GeV to 100 TeV. I use 30 energy beams. I do the spatial selection using celestial coordinates. The name of the source that I am interested in is the crab. I give the coordinates here. I choose a radius for the on region, which is 0.2 degrees, and I use a background method which is called reflected, meaning the background, if you have the source position and the pointing position, the off positions will be reflected with respect to the pointing position, is what was shown in the slide that I had in my presentation. So this has already been run. So now we have our on-off observations. We can look at them. So you see that now we have one observation, which is of type CTA on-off, and you have the on time, the live time, and you have the properties of the on-off response, which is called RMF and PHA. And we still have our models that are now only including the crab nebula itself. This is because I use a parameter value here, which is use background model, which is set to false. In this case, it means that I decided to treat the background as a nuisance parameter that will be determined directly by the fit based on the off events. You are not obliged to do that. If you want, you can still do an on-off observation, but assuming a background model. That is a possibility if you want. Now, I can pass my on-off observations to CityLike, run my likelihood analysis, and here you will see that we have obtained, again, a converging likelihood analysis. And now we have our parameters for the Crab nebula that were determined again to be compatible with the input values. And that's all. Of course, also in this case, you should check the residuals. For an on-off analysis in spectrum, you can only check the spectral residuals, not the spatial ones, because there is no more spatial information. But you should check the spectral residuals, which I have not done here, but you can do exactly as we did before. Are there any questions on these last steps or on the demonstration in general? Also, practical questions before you move on to do the practical exercises. Okay, so let me share again the name of the exercises. So now all of you should choose an exercise to do, and I will go to create breakout rooms and assign all of you to a breakout room depending on the exercise. So I would ask you to type in the chat window your name as it appears on Zoom and the number of the exercise that you want to do. If you have not installed Ctools on your machine, and so you are going to install Ctools and retrieve all the data, please type 0 so that I put you in a separate, or actually type 0 and I will leave you in this general room. Was that clear? So what, okay, perfect. I see that people started doing it. Okay. I need to stop sharing in order to do that. I hope that you have so I need the 6 breakout rooms. Okay, that will take me a little time, so be patient. But in the meantime, get started with your exercise if you want. Did everybody get the Jupyter notebooks that I had asked you to download as a guide for the exercises? If there is someone that doesn't, please let me know. Maybe speak rather than writing in the chat, because right now the chat is very busy.
Sorry, could you repeat what thing do we need?
In the material that I sent for the school, there was there were some notebooks with the exercises. So that's the thing that I was asking you to start working on. Did you download the material already?
Ah, yes, this zip material Ctools is
Yes, yeah.
okay.
Inside
Yes.
inside that folder, you will find some Jupyter notebooks, one for each exercise. So you can start working on that, or there is a PDF as well.
Okay.
Okay, I see that there are many people that didn't indicate in which room they want to go. So does that mean that you want to stay here because you still need to install the tools? And Sergio should be able to also move from one room to the other. So can I ask the host, please, to make also Sergio Hernandez Cadena a co-host of the meeting?
Sure, I'm doing
Thank
that.
you so much. So Sergio, perhaps you can start going around between the rooms where there are already some people while I take care of splitting people between rooms and help those that need assistance to install here.
Okay, yeah, no problem.
Thank you so much. For the people that are still here, if you need help with installation, let me know. If you want to be dispatched into a room, let me also know. Okay, otherwise I will go myself to see how people in the rooms are doing.
Okay, I'm staying here in case.
Okay, thanks so much.
Are we supposed to have been assigned a room already? Because I can't see that I have been.
Yes. Do you want me to ask the speaker to assign you to a room, or I can ask maybe assign you? Which room do you want to go?
Number 2.
Okay, let me try to do that.
ব্রেক দিল 10 মিনিটে দেখি আমাকে একটা 10 মিনিট এখানে ব্রেক